All right, geometry class, let's continue in this unit on coordinate geometry and polygons. Today what we're going to go over is polygons in the coordinate plane. Now what should we already know? We should already know about linear equations and slope of lines, especially vertical and horizontal stuff, parallel and perpendicular as well, because that all ties in here. If you don't know that stuff, well, don't even start this lesson. Go back into my playlist on YouTube and watch everything else, because we're going to talk about polygons in the coordinate plane. So what are we going to learn about? We're going to learn about classifying a triangle, classifying a parallelogram, and classifying a quadrilateral. So what does that mean? That means we have to remember all this stuff from the previous unit, all the different quadrilaterals that we have, what makes parallelograms awesome, what makes rectangles, rhombuses, squares, trapezoids, isosceles, trapezoids, and kites. We have to know all that stuff. So if anything I cover here is challenging, make sure that you're going into the previous units and making sure that we understand all that stuff, because we're going to get into that. Now, in order to classify everything, we have to know a few pretty awesome notes, like old stuff. The distance formula, the midpoint formula, and the slope formula. And if you know me or have heard me talk about this stuff before, I'm not a big fan of the formulas because I just use things, right? So the distance formula, what does it say? It says subtract the x's, square them. Subtract the y's, square them. Add that stuff and take the square root, distance formula. Okay, so you don't need to memorize d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Yeah, you can memorize that, but the more you use it, the more you realize you don't need it. Just subtract your x's, subtract your y's, square those things, add them, take square root. It's all related to Pythagorean theorem. So why are we going to be using that? Well, we're going to be using that to determine whether sides of a polygon are congruent. Okay, we're also going to use that to see if maybe diagonals are congruent, because what do we know about congruent diagonals? Rectangle. Oh yeah, I remember that, right? So all this stuff comes back. So we're going to be using the distance formula. We also have the midpoint formula. Again, you can memorize this stuff if you want. Midpoint is x1 plus x2. Nope, it's the average x coordinate and the average y coordinate. That's your midpoint formula. And what will we be using that for? To determine the midpoints of a side and to determine where stuff bisects. Okay, because the bisect, it's the middle point, right? Midpoint. And then lastly, slope formula. And again, y2 minus y1 over x2 minus x1. Rise over run. Change in y over the change in x. Now, what are we going to use that for? Parallel lines for parallel sides, and perpendicular lines for right angles. Okay, perpendicular lines are all about right angles. So we'll be using all that stuff. Okay, and this whole lesson is really practice, practice, practice. We're going to be using these a whole bunch. So the more you use it, the better. Let's jump into some questions. So we're going to classify a triangle first. So here's this triangle we have given on a grid. We're going to determine if it's scalene, isosceles, or equilateral. Cats, what in the world are those words? So we got to know what scalene means. Scalene means there are no congruent sides. Isosceles comes back. Remember what isosceles triangles are. Isosceles have two congruent sides. And then equilateral, remember that comes back. Equi, same as lateral side. So same side, three congruent sides. So we have to classify this triangle. Now, how in the world are we going to do that? We have three sides. How can we tell if any of those sides are congruent? Well, we can measure those sides, right? So what is our measuring tape? The distance formula. So the distance formula acts as our measuring tape. We can measure the sides by using the distance formula. So again, here's that formula. Do you have to memorize it? No, let's see how I use it. So we have our three sides, which means you have three coordinates. So the coordinates for our point A here, if you don't know, the coordinates are 0, 1 for A. For B, it goes all the way up to 4, 4. And then for C, we have a coordinate at 7, 0. So hopefully you can see that's what's happening with our three coordinates, and now we can use the distance formula. So if I talk about measuring from A to B first, if I talk about measuring from A, how am I going to measure from A to B? Well, I'm going to use the distance formula. I'm going to square root some stuff. I'm going to subtract my x's, 4 minus 0. And I'm going to square that. I'm going to subtract my y's. 4 minus 1. And I'm going to square that. And I'm going to add them. Okay, so that's how we use the distance formula. Again, there's that formula. Can you memorize it? You can. Subtract your x's, square them. Subtract your y's, square them. The rest is number crunching. All right, so we're going to do that. So we have 4 minus 0, which is 4. I hope you know that. And then 4 squared is 16. And now we're going to add that to 4 minus 1 is 3. Hope you know that. And then 3 squared is 9. So we have 16 plus 9, but the square root of all that. 16 plus 9 happens to be 25. And if you recall the previous video on simplifying square roots, we know that the distance from A to B now is the square root of 25, which is 5. So the measuring tape that we have used, the distance formula, has told us that from A to B is 5. So can we tell now if this triangle is scalene, isosceles, or equilateral? The answer is no, we can't. So here's where you throw your hands up in defeat. And you say, Cats, are you for real? I have to do this same thing for B to C and from A to C? And my answer to you is yes. Get over it. Let's do it. Okay, so we're going to get over that little thing, and yes, we're going to do it. So now we have to find the whole same thing for B to C. So from B to C, we do the same process. Square root of, subtract my x's, 7 minus 4, and then we're going to square that, and subtract my y's, 4 minus 0, and then square that. Wait, Mr. Katz, the formula clearly says x2 minus x1 and y2 minus y1. Clearly says that. You did this one minus this one, and then this one minus this one. My argument to you is that it doesn't matter. See if you can tell me why. Do you give up? Good, because we're squaring stuff. What's a negative times itself? Positive. What's a positive times itself? Positive. So get over it. The more you know stuff, the easier things are, right? So pay attention. So it doesn't matter if I do 7 minus 4 and then 0 minus 4, or 4 minus 7 and 4 minus 0. It doesn't matter because we're squaring it. Okay, so you got to know some things about some stuff, and life becomes easier. Anyway, 7 minus 4 is 3. 3 squared is 9. I hope you know that. 4 minus 0 is 4. 4 squared is 16. Hey, this is looking familiar, dude. Right? Doesn't it look the same? So we have the square root of 25. So this side is also 5. That's pretty cool to know. Isn't that neat? So from B to C is 5 also. So do we now know if this triangle is scalene, isosceles, or equilateral? Not quite yet. We don't know from A to C, but we certainly now know. We now know this is not scalene. So we got to do another one. We're going to find out from A to C, right? So now we have to find out from A to C. So from A to C, right? So subtract my x's, 7 minus 0. Subtract my y's, 1 minus 0, and hopefully you can already tell this is not equilateral, right? Hopefully right now you can stop and say, well, this clearly is not going to be 5, right? So you can take a mental note. We can already tell it's not going to be 5. Okay, so we can already tell that this is going to be an isosceles triangle, but let's finish the math because practice is awesome. So 7 minus 0 is 7. 7 squared is 49. And then 1 minus 0 is 1. 1 squared is 1. So we have the square root of 50. Okay, now we can clearly tell that the square root of 50 and the square root of 25 are not the same. But remember the video again on simplifying radical expressions. How do we simplify the square root of 50? If you recall, 50 is 25 times 2. So we have 5 times the square root of 2. Okay, so we do have 5 times the square root of 2. In fact, this is a pretty special triangle, believe it or not. We can talk about that later. So we know the distance from A to C is not 5. It's 5 times the square root of 2. Okay, and this is, by the way, a 45, 45, 90-degree triangle. But anyway, not the point. The point is this is not scalene. It's not equilateral. This is indeed an isosceles triangle. Okay, so we have 2 congruent sides. How did we know? We used our measuring tape. What is our measuring tape? The distance formula. Okay, so that's how that works. Are we done yet? Nope. We're going to do it again. Let's see how fast we can start doing this stuff. Okay, so let's do another example, and then we'll see if we can do it a little bit quicker. All right, so we're going to classify this triangle now. Is it scalene, isosceles, or equilateral? So what do? Let's get our ordered pairs down. Our ordered pair for A. Oh, you cats, really? Negative numbers? Yup. Get over it. So this ordered pair is negative 5, 2 for our point A. For point B, our ordered pair is 4, 4. I guess point B likes being at 4, 4. And then our point C is going to be at 2, negative 5. Okay, so now what we're going to do is measure. We're going to use our measuring tape, which is the distance formula. I like to keep things a little bit organized, so I'm going to label my first measurement from A to B. Now watch how fast I can do this. I'm going to actually write this out because I know you guys love negatives. We're going to subtract our x's. Listen carefully. Negative 5 minus 4. That's subtracting our x's. Negative 5 minus 4. And then we're going to subtract our y's. 2 minus 4. Okay? So now we can simplify that. Now, what is negative 5 minus 4? If you tell me negative 1, I'm going to smack you. It's actually negative 9. Okay? So negative 5 minus 4 is negative 9. Negative 9 squared is 81. All right, so now we have 2 minus 4 is negative 2. Negative 2 squared is positive 4. So 81 plus 4. This is the square root of 85. Okay, now can we simplify that expression? Is that possible? Well, 85 is 5 times 17, so no. This is as simple as we can get it. So we now know the distance from A to B is the square root of 85, right? It's 9 and change, 9 point something. So we know it's a little bit more than 9. But that is our measurement from A to B. Well, what about from, let's say, B to C could be next. Why not? So let's measure B to C. Use our measuring tape, distance formula. Boop. Subtract our x's. 4 minus 2 is 2, right? 4 minus 2 is 2. 2 squared is 4. Look how quick that happened. Now we're going to subtract our y's. 4 minus negative 5. 4 minus negative 5 is 9. 9 squared is 81. Okay, so once again, 4 minus negative 5 equals 9. Goofballs. All right, so make sure you don't make those simple mistakes. You don't want to do that. So now here again, we have the square root of 85. Funny enough, from B to C is also the square root of 85. So we know that. So there goes scalene out the door. All we need now is from A to C. And again, I like to keep myself organized. So how fast can we go? Negative 5 minus 2 is negative 7. 7 squared is 49. And then our y's. 2 minus negative 5 is 7. 7 squared is 49. So we have the square root of 49 plus 49 is 98. Can we simplify that? Possibly. Does 4 go into that? No. 2, let's see. 2 is 49. Oh, yeah, it's 7 root 2. Anyway, but that's not the point. So it's not the square root of 85, right? So we know it's not equilateral. So this is also isosceles. That's interesting. So two congruent sides gives us isosceles triangle. So that's how that works. Let's do another one. I'm not done with you. Practice, practice, practice. All right, so let's take a look at this one now. Where's my graph? Cats, where's my graph? I'm not giving you one, punk. Look, here's an ordered pair, here's an ordered pair, here's an ordered pair. Is it scalene, isosceles, or equilateral? So we're going to do the same thing we've done before. We have to have 3 sides. Let's organize our sides, right? What about from D to E? Okay, so that's how we're going to organize this. We can also look at ordered pairs without doing anything else. So from D to E, I'm dealing with these 2 ordered pairs. Subtract my x's. 0 minus 1 or 1 minus 0 is 1. 1 squared is 1. Subtract my y's. 0 minus 4 or 4 minus 0 is 4. 4 squared is 16. So we have the square root of 17. So we know from D to E is the square root of 17. Well, what about from E to F? Let's do the same thing. Now we're going to look at E to F. Subtract my x's. 5 minus 1 is 4. 4 squared, 16. Now subtract my y's. 4 minus 2 is 2. 2 squared is 4. Square root of 20. All right, so these 2 are way different. Fair enough. We're like on track for a scalene triangle. Well, I'm missing a side. We got D, E, and EF. What are we missing? We're missing DF. So we can calculate our third side, DF. Look how fast we're using the distance formula now. So I have 5 minus 0 is 5. 5 squared is 25. I can already tell it's going to be a scalene triangle. 2 minus 0 is 2. 2 squared is 4. So we have the square root of 29. 3 completely different side lengths. Okay, so our measuring tape comes up with 3 completely different side lengths, all different, no congruent, scalene, And that's how we can classify triangles. Okay, so we use our distance formula, our measuring tape. We'll start using this a lot just as fast in other things as well. Let's take another example of something else now. Now we're going to classify a parallelogram. So the question is parallelogram ABCD a rhombus? Explain. What do we know about rhombuses? We know actually two things about rhombuses. Remember good old rhombus? Yeah, rhombus. We know two things. All four sides are congruent, and the diagonals are perpendicular. Okay, so we got to know some things about rhombus. Now, oh my gosh, if I ever catch you saying this, I'm going to lose my mind. Don't ever say it's a rhombus because it looks like one. Never judge anything or anyone based on looks. You're welcome. So we got to know something about a rhombus. A rhombus has four congruent sides, and a rhombus also has perpendicular diagonals. So there are a couple things that we can do. Now, we can't just base it off of the diagonals because a rhombus is not the only thing with perpendicular diagonals. Perpendicular diagonals also exist in a kite and a square. So we can, feel free, to determine whether or not these are perpendicular, slope, but the best thing to identify a rhombus is four congruent sides. So guess what we have to do? Good guess. We have to use our measuring tape. Here's our measuring tape, distance formula, 4 times. So let's rock this thing out. Remember, I like to keep things organized. So I'm going to measure AB first. So from A to B, -2 minus 0 is -2. Square that is 4. Positive, right? And then my y-coordinates, 0 minus 4 is 4. 4 squared is 16. So from A to B is the square root of 20, which is, by the way, 2 root 5. But that's not the point. How about from B to C? So from B to C, we got 0 to 4 is 4. 4 squared is 16. And then from 4 to 5 is 1. 1 squared is 1. Squared is 17. Do we have to continue going? No. Because these two are different. BC and AB are not the same. A rhombus has 4 congruent sides. So we already can tell the answer to this is no, because AB and BC are not congruent. Okay? Not congruent. So no, not a rhombus. So we have to remember some stuff from the previous unit. All right, so we can stop right there. What if they were the same? Keep going. Use the measuring tape. But we said it's a parallelogram. So if it's a parallelogram, we know AB and DC are congruent, and we know that BC and AD are congruent. So we can stop right there. Let's do more. So here's another one. Parallelogram MNPQ has these vertices. Is it a rectangle? Ooh, now we have to explain. Rectangle. What do we know about rectangles? Rectangles have 4 90-degree angles, okay? And they also have congruent diagonals. So what can we do? We can do a few things here. So we got to remember some stuff about rectangles. Rectangles means 4 right angles. So how can we tell now if something is a right angle? So let's do this. How can we tell if we have 4 right angles? Slope. Remember, if we have perpendicular slopes, if you recall, opposite reciprocal, okay, opposite reciprocal slopes, those then are perpendicular lines. So let's do that. Let's tell if these have opposite reciprocal slopes. So if we have a basic rectangle, and we call it MNPQ, can we tell if we have 4 right angles? Okay, so that's what we're going to figure out. How's that going to work? Well, we have to find the slope of MN and compare it to the slope of NP. Okay, so we look at the slope of MN and compare it to the slope of NP. If we have opposite reciprocal slopes, we have perpendicular lines. And if we have perpendicular lines here, then we know the whole thing is a rectangle because we have a parallelogram. Okay, so let's play this out. Let's find the slope of mn. Here's mn. Now, how do we find slope? Again, you can use that formula, right? You can use the slope formula. I'm going to use something different. I'm going to use just words. The change in y over the change in x. Okay, the change in y over the change in x. Now, this one, order does matter. I'm not squaring anything, so order does matter. So I'm looking at the change in y from n to n. I'm going from 1 to 4. Okay, 1 minus 4. And then I look at my change in x, 0 to negative 1. So 0 minus negative 1. So the slope of mn is going to be negative 3 over 0 minus negative 1 is positive 1. So my slope of mn is negative 3 over 1, or just negative 3. I'm going to compare that to the slope of np now. Okay, so now I'm going to look for np. Here's n, here's p. Let's do the same thing. The change in y over the change in x. So if I'm going to go from n to p, here's n, here's p. Change in y, 4 minus 5. And my change in x, negative 1 minus 2. Negative 1 minus 2. So 4 minus 5 is negative 1. Negative 1 minus 2 is negative 3. Now, I have negative 1 over negative 3. But what's a negative over a negative? A positive. So the slope of NP is positive 1/3. Now we have to look at the relationship between these two slopes. Are they opposite reciprocals? Okay, if I flip one and change the sign, do I get the other one? And again, if you did not see the previous videos on parallel and perpendicular slopes, you're not going to be able to do well with this. Clearly, these are opposite reciprocal slopes. They are indeed opposite reciprocal slopes. So what does that mean? That means the two lines are perpendicular. That means we have a right angle. So yes, indeed, this is a right angle. So yes, a right angle. So if this is a right angle, then we have a rectangle. How do we know? Because it's a parallelogram. If this is a right angle, then we know the opposite angle is a right angle. We also know that the consecutive angle is supplementary, so we do have 4 right angles. Okay, so yes, this is a rectangle. Yes, this is a rectangle. MN to NP, opposite reciprocal slopes, 4 right angles. We are set to go. Okay, so this is indeed a rectangle. That's how we can classify a parallelogram. So, what about classifying some interesting quadrilaterals now? So now we start using, we haven't used midpoint yet. We're about to. So a kite is shown at the right. What do we know about kites? If you recall, kites have no pairs of parallel sides, but 2 pairs of consecutive congruent sides. Okay, so we know that these 2 sides are congruent and these 2 sides are congruent. So the question is, what is the most precise classification of the quadrilateral formed by connecting the midpoints? So now we have to calculate midpoints. Okay, so there's an easy way and a hard way. So let's take a look at our points. We're going to connect the midpoints. Our ordered pairs for k is at negative 1, 2, 3, 4, 0. Our ordered pair for I is at 0, positive 4. Our ordered pair for T is at 8, 0. And our ordered pair for E is at 0, negative 4. 1, 2, 3, 4. So we can find the midpoints of each side. The midpoint from K to I. How do we find midpoint? Average X, average Y. Okay, so that's how I look at it. The average X and the average Y. Or you can follow the formula. It doesn't matter to me. So if we look at from K to I, we see that one X is negative 4, the other X is 0. So the average X is negative 2. The average Y is from 0 to 4. So the average Y is positive 2. So we have negative 2, positive 2. Look here. We can clearly see that's also the midpoint. Here's a distance. We can count this distance. 1, 2, 3, 4 units. If it's 4 units, midpoint is halfway there. Can we do the same thing from I to T? Quite possibly, but let's do our averages, okay? So we have from 0 to 8, the average x is 4. From 4 to 0, the average y is 2. So we have a midpoint at 4, 2. There it is. And we can do the same thing down here. From 0 to 8, the average is 4. And then from 0 to negative 4, the average is negative 2. So at 4, negative 2, midpoint here. And now, from k to e, the average x from negative 4 to 0 is negative 2. And the average y from 0 to negative 4 is negative 2. So negative 2 is down here. So we have found our midpoints by using the shortcut of the formula. But what are we doing? We're formed by connecting the midpoints. So we have a line segment here, and a line segment here, and a line segment here, and a line segment here. So what is the most precise classification of this thing we just drew? Doesn't it look like a rectangle? And the answer is, yeah, it kind of does, but let's be sure. Let's be sure. So let's do what we can to classify this. Well, we have a distance here of 1, 2, 3, 4 units. We have a distance here of 1, 2, 3, 4, 5, 6 units. We have a distance here of 1, 2, 3, 4 units. And a distance here of 1, 2, 3, 4, 5, 6 units. So we definitely have a parallelogram, right? So far we have established parallelogram, okay, because we have two pairs of congruent opposite sides. So we have a parallelogram. Is it a rectangle? Well, let's take a look. Do we have 90-degree angles? Well, let's take a look at our side here, right? From this midpoint here, we have our ordered pair at negative 2, negative 2, and negative 2, positive 2. The x-coordinate is the same. If the x-coordinate is the same, we have a vertical line. Okay, so that video, again, previous video, vertical and horizontal lines. The x-coordinate is the same with a vertical line. What about from this point to this midpoint? Our y-coordinates is the same, so here we have a horizontal line. And if you don't know that's a horizontal line from the y-coordinates being the same, again, the previous video. So guess what? Perpendicular. Vertical is perpendicular to horizontal all day, every day. If it's a right angle here, it's a right angle everywhere. We have a rectangle. That is the most precise definition of the quadrilateral formed by connecting the midpoints of this kite. It is a rectangle. So let's do some more, and let's see if we can go a little bit quicker. The most precise, again, same question. The most precise classification of the quadrilateral formed by the four segments connecting midpoints of the sides of the square. So let's look for the midpoints. So now watch this square. From D to A, check it out. It's 1, 2, 3, 4 units, midpoint right in the middle. From A to B, 1, 2, 3, 4 units, midpoint right in the middle. From B to C, 1, 2, 3, 4, and 1, 2, 3, 4. So we have our midpoints. We connect the midpoints. Guess what we have? Okay, looks like we have another square, right? So is that the case? 1, 2, 3, 4 units up top. 1, 2, 3, 4 units down the side. 4 at the bottom, and 4 on the other side. So we definitely have 4 congruent sides. It's a rhombus, no doubt. But we have a vertical line and a horizontal line. Vertical and horizontal are always perpendicular, so we have a square. We have 4 congruent sides and 4 right angles. We have a square. So you see how fast that can go if you know what you're doing. Life is easy when you know what you're doing. I hope you agree. All right, last question. Classifying a quadrilateral. An isosceles trapezoid now has vertices 0, 0, 2, 4, 6, 4, and 8, 0. What special quadrilateral is formed by connecting the midpoints? We don't have a picture. How do we do this? Well, we can do this by finding the midpoints. What's the midpoint of A and B? Okay, so the midpoint from A to B. The average x from 0 to 2, the average x is 1. The average y from 0 to 4 is 2. We got that. That's one of the midpoints. What about the midpoint from B to C? So the midpoint from B to C, from 2 to 6, what's the average? 2 plus 6 is 8, divided by 2 is 4. So the average x is 4. Our y-coordinates are 4 and 4, so the average y is 4. Well, that's interesting. Isn't this a horizontal segment? Yeah, that's horizontal. So we should know that, but we'll get there in a second. What about the midpoint from C to D? The midpoint from C to D now, we have from 6 to 8. 6 and 8 is 14. Divide that by 2 is 7. The average x is 7. And the average y from 4 to 0 is 2. So we have our midpoint there. Now notice what just happened. Look at our midpoints. We have the same y coordinate. So the midpoint from A to B is a horizontal line, the same y coordinate. We're only missing one more midpoint. The midpoint from D to A or from A to D. So the midpoint, the average x is 4. From 0 to 8, the average x is 4, and the average y is 0. So look what's happened here. We have the same x coordinate from these two midpoints. That is a vertical line. So from A to B, we have a horizontal line. The y coordinates are the same. And from these two midpoints, we have the x coordinate is the same. That's a vertical line. So we know we have perpendicular stuff going on. So let's visualize what we have. We have a point at 1, 2, which is about here, a point at 4, 4, which is about here, a point at 7, 2, which is about here, and a point at 4, 0, which is down here. So it looks like, but those aren't necessarily connected. So from midpoint from A to B is at 1, 2. The midpoint from B to C is at 4, 4. 2, 3, 4, 4, 4. And C, 5, 6, 7. And we have our points here. So what is going on with these 4 points? What's interesting is that we have from 1, 2 to 4, 4 goes here. From 4, 4 to 7, 2 goes here. And from 7, 2 to 4, 0 goes here. But these two things that we've noticed are not connected. Okay, 1, 2 and 7, 2 are not connected. So what do we know? We know that the diagonals are perpendicular. If the diagonals are perpendicular, we have a rhombus. Isn't that strange? So how far is it then from 1, 2 to 4, 4? We can calculate the distance. From 1, 2 to 4, 4, subtract our x's. 4 minus 1 is 3. 3 squared is 9. Subtract our y's. 4 minus 2 is 2. 2 squared is 4. We have the square root of 13. So our distance from here is square root of 13. Well, what about from 4, 4 to 7, 2? Okay, so now we're going to calculate the distance from 4, 4 to 7, 2. 7 minus 4 is 3. 3 squared is 9. 2 minus 4 is 2. 2 squared is 4. Square root of 13 goes here as well. It looks like we're going to have a rhombus, right? So let's be sure. What about from 7, 2 to 4, 0? Well, from 7, 2 to 4, 0. Let's calculate that as well. 7 minus 4 is 3. 3 squared is 9. 2 minus 0 is 2. 2 squared is 4. Once again, square root of 13. And if this is well, we don't know if it's a parallelogram, do we? No. So let's calculate one more time. So from 4, 0 back to 1, 2. From 4, 0 to 1, 2. 1 minus 4 is negative 3. 3 squared is 9. 0 minus 2 is 2. 2 squared is 4. Once again, square root of 13. So what just went on? We have perpendicular diagonals. All 4 sides are the same. What is the special quadrilateral formed? A rhombus. And that's how we can tell. We use our measuring tape, and we use the qualities of parallelograms that we know, and we can figure out all these fun questions. So that's it for the unit. We can use all sorts of, or that's it for the lesson. We can use our measuring sticks and coordinate geometry and some algebra, and we can figure out a whole bunch of stuff. So I'll catch you on the flip side where we do some more coordinate geometry. I hope you enjoyed the lesson. Bye.